So this one, I find this one actually extremely, really difficult to explain because it's so hard. However, oh, by the way, if everyone has trouble with the slides, they're in the chat currently. So if you want to have a look at the slides, they're right there. So, Equilibria, the reversible reactions. This is quite important to understand, so I'll try to explain this as much as I can, but this is a very hard thing to grasp. So don't worry, I'm going to slowly explain it. If you have any questions, ask. Okay. In a reversible reaction, so when something's at equilibrium, basically, A plus B goes to C plus D. Let's say that's the equation. In a reversible reaction, the reactants can form the products, and the products can form the reactants. I know that technically means that they're both reactants and they're both products, but the stuff in the front is the reactants. The stuff at the right side of it is going to be the products. And reactants can form the products can form the reactants. That's what's happening in a reversible reaction. When something is at equilibrium, it means that the rate of reaction is going to be the same forwards and it's going to be the same backwards. So so this is kind of just the same. Rate of reaction forwards, the rate of reaction of the reactants forming the products is going to be the same as the rate of reactions forming the rate of reactions of the products forming the reactants. There's going to be the same forwards and backwards. That's when equilibrium is taking place. And mind you, when I'm talking about this, it means that it's taking place in a closed system. That means that the reactants and the products cannot escape. I know a lot of people are talking about asking for the slides. We will send them to you. We will send them to you even if you can't see them. We will figure this out at the very end of it. So anyway, yes. So, right. However, it's important to note that even at equilibrium, the direction of the reversible reactions can change according to the different conditions. And the conditions could be things like temperature, things like pressure, or concentration. And we will look through that through Le Chatelier's principle. Okay. So the Le Chatelier's principle and understanding equilibrium is that the conditions in a reversible reaction, whatever is forward is going to be the opposite backwards. If forward is endothermic, backwards is exothermic. I'm hoping that makes sense. Let's talk about Le Chatelier's principle, and let's talk about the three things: concentration, temperature, and pressure. A change in concentration, it will depend which direction your equilibrium is going to go at. So if I have more reactants, if the concentration of reactants increases, you're going to have more products because you're trying to balance it. Think of it like a balance. So you see the diagram on the bottom right? Think of it like a balance. If there's so much here, you want to balance it back by creating more here. So if a concentration of a reactant increases, products are going to increase. If the concentration of a product decreases, if this goes down, more of this is going to react, so this will go back up. That's the understanding of concentration in equilibrium. So that's concentration. Temperature. Temperature, if it increases, it's going to go towards the endothermic direction. And if it decreases, it's going to go towards the exothermic direction. When you're given a question, either they will tell you which direction is exothermic and endothermic, or you have to figure this out on your own by looking at the numbers. So they give you the reaction. And if the forward reaction, for example, is negative something joules, if it's negative, it's exothermic. If it's positive, endothermic. So if, let's say, the forward reaction is a positive number, like something joules, 56 joules. If the temperature increases, it's going to go towards the endothermic reaction, meaning it's going to go towards the forward reaction because the forward reaction is endothermic. I'm going to reword that. Again, that was very wordy. Temperature increases towards endothermic. Temperature decreases, goes towards exothermic. To figure out whether something is exo or endothermic, either they'll tell you in the question or they will give you the energy. And the energy, if it's negative, it's exothermic. If it's positive, it's endothermic. So be careful with the question. That's temperature. Now for pressure. If the pressure increases, this is where it's a bit confusing, it's going to shift towards the side with the smaller number of molecules. So let me just type this out because it's kind of hard to explain just by that. Right. Let's say I have A plus A plus B gives you, that's not actually equal, let's just pretend that's the reversible sign, 2C plus 3D. In this situation, in this situation, there are more moles on this side than on that side by looking at the number in front. There are 5 moles on this side, 2 moles on this side, because there's 1 and 1, 2 and 3. If there's an increase in pressure, it's going to shift towards the side with the less number of molecules, less number of moles. So if I increase the pressure, the equilibrium is going to go towards the A plus B side. If I decrease the pressure, it's going to go towards the side with more molecules, the 2C plus 3D side. I'm hoping that is clear. Oh, okay. So that is that. Okay. Any questions regarding that so far, or should we move on because there's more on equilibria? Okay. Doesn't seem like anyone has any questions. We'll move on. There are a few questions regarding equilibria. I do want to have a look at that. So I want everyone to just have a look at the I want everyone to have a look at this question. I'm going to give you guys maybe 30 seconds to look through it, and then we'll kind of walk through it. Have a look at all of these questions. Please have a look at all of them, please. Okay. To understand this, first of all, let's just look at the question. It's telling you that the equation is from 2NO2 and it goes to dinitrogen tetroxide, which is N2O4. The 4 reaction, it tells you it is exothermic. So it's asking you what's the color of the mixture when a new equilibrium reaction is reached. Sorry, I forgot to give you this extra information. It's asking you what happens when my bad, but it tells you, it's asking you, it increases the pressure in the gas syringe. So what happens when you increase the pressure in the gas syringe? What is the color of the mixture? Well, as I said, when you increase the pressure of the gas syringe, when you increase pressure just in general, it's going to move to side with the less molecules. And because it's going to move to side with the less molecules, it's going to go to the colorless side. So therefore, the mixture is likely going to be a lighter shade of brown because it's going towards the colorless side. On that side, there's less molecules. Now let's look at number 9.5. What is the effect of increasing the pressure on the equilibrium position of this reaction? Again, with pressure, we're looking at the number of molecules in front. So on the left side, the reactant side, there's 2. On the right side, there's also 2 because H2 has one in front, I2 also has 1 in front. That means that increasing the pressure isn't going to do anything because they both have equal number of molecules on each side. So your answer would just be there's no effect because there's equal number of moles. Final question, effect of adding a catalyst. I have said that adding a catalyst does increase the rate of reaction. However, I never said it affected anything on equilibrium position. I told you that in equilibrium and in a reversible reaction, rate of reaction is the same forwards and backwards. Therefore, adding a catalyst will not affect the equilibrium position. This is a bit of a cheeky question, and sometimes they do ask you this. So please make sure that you know that when you're talking about equilibrium and you're talking about increasing rate of reaction, if you do add a catalyst, rate of reaction might increase, but it increases both ways. Therefore, there is no effect on the equilibrium position. I'm hoping that is clear. any more questions regarding this because we are going to be moving on from equilibrium to organic chem.